Hello, my name is Marvin Hofer. I'm studying at the University of Leipzig and work at the Institute for Applied Informatics. In this talk, I want to present the new DBpedia release cycle. But what means the new in the new DBpedia release cycle? So currently we can achieve over 21 billion facts per month as RDF triple, and therefore we have monthly releases of the mapping-based, generic and Wikidata extraction. The text extraction, for example containing the abstracts of the page articles, is extracted every third month during their complexity. We also rely now on a more improved testing methodology and a Marvin pre-release bot. The testing methodology consists of 7 different levels. So we have unit test, custom rules, syntax validation, shape expressions and sparkle tests on the produced metadata and the data itself. Also we are focusing on a Minidump approach and a large-scale evaluation based on this testing library. Finally, we provide a better access for the community, and therefore we have a better process transparency, more accessible error reports, and a direct linking of issues and tests. We also follow now new conceptual design principles. The most important one is the time-driven data release approach. Therefore, with the Marvin release bot, we automated the extraction process for more frequent data releases. This comes with the subordination of software, so we don't wait for features to be implemented, we just use the latest commit in the DBpedia extraction framework to start a new release. Also, the produced data is automatically delivered on the DBpedia Databus. Moreover, we focus on the traceability and issue management of our produced data. Therefore, we can use stable databus identifiers to semantically pinpoint produced data files with issues, and also the explicit association of data artifacts and code fragments or classes. The new Minidump approach can also be used for more fine-grained issue management and error handling. The fixed time-based release cycle works as follows. The Marvin release bot pulls the latest commit of the DBpedia extraction framework and also downloads the latest Wikipedia dumps. Then the extraction is run and the produced raw release is deployed in the DBpedia databus. After this data is syntactically parsed and errors and warnings of these triples are pruned, and a clean and sorted data release is published under DBpedia on the DBpedia databus. This release then is used in the large-scale validation, and these reports, also the reports of the syntax validation, are provided to the community for reviewing. Based on these reports, issues can be created and data artifacts can semantically pinpointed to this issue. Based on these issues, new tests can be created for the Minidump and the test library can be adapted. The test library for the Minidump and the large-scale validation is the same. After each month, the cycle starts over again. With the Minidump and large-scale evaluation, the whole cycle is now more a test-driven knowledge extraction. The Minidump is a small dump of URIs from Wikipedia pages or articles. And the Minidump tests are used for a continuous validation at a git commit based on CI tools like Travis or GitHub Actions. The Minidump and large-scale evaluation process is divided into 4 steps. At the first step, the Minidump is expanded with Wikipedia page articles that contain a data issue after the extraction. In the second step, tests can be defined related to this issue, for example with Shackle. With the help of the Minidump and the defined test, the DBpedia extraction framework can now be improved to fix this data issue. Later then, post-release, the same testing library is executed again to test the whole data of the introduced improvements. The testing library is divided into 7 methodology levels. So we have well-known levels as unit tests, integration tests, and syntax parsing. For the software level, we use unit tests to test data parsers or extractor methods. The second level is a newly introduced and is named the construct validation. Therefore, we can define custom rules for RI patterns, encoding errors, datatype or literals, and also the correct usage of schemas or vocabularies. This step is independent of the strict syntactical correctness of the whole data. In the next step, the syntax parsing is used to check for errors or warnings in the produced triples. With shape expression, by using Shackle, we can check, for example, domain and range constraints in the extracted data's graph structure. In the last both levels, we can sparkle over the metadata or on the extracted graph itself to test, for example, the release completeness or other things on the consumer side. Let me introduce the construct validation approach. Therefore, I will define what a construct is. A construct can be any character or byte sequence, typically part of the EBNF grammar. So for example, for RDF, this could be the subject, property or object part, and therefore it could be an RI, literal or blank note. Blank notes are ignored due to their not standardized way of their serialization. Then, for this construct, a test can be defined. For example, for an IRI, a trigger can be defined that checks for the namespace, and based on this namespace, a test can execute it, for example, to check if the correct URI path segments in this IRI, or the right encodings or usage of characters in this IRI, for example, with regular expressions or other string matches. For this test, we define coverage metrics, in our case for RIs and literal patterns in RDF, to analyze the coverage of these tests in our whole datasets. A test of this construct is independent of the inaccuracies in the rest of the data. That means, for example, the subject, property or object part can be tested independently of the rest of the data. The construct validation is currently implemented based on Apache Spark and can be used to validate flat turtle files or entropy files. Let me explain on an example why this construct validation is important. So we had a problem and an issue that in the produced data of 2016 and 2019, the RDF langstring literals were stated explicitly with this RDF langstring data type. Considering the standard, the RDF langstring is an implicit type and must never be serialized. This issue couldn't be catched with the Apache Jena parser, and therefore we defined the construct validation test. The test case is defined as follows. So we have a trigger that triggers on every literal that has the RDF langstring data type serialized, and the validator just returns false, because if this exists, then it's false. And as you can see, in 2020 March, we solved this issue, and in the April release of 2020, the issue disappeared. If you want to know more about the currently defined construct validation test cases, you can visit the Extraction Frameworks resource folder. Let's demonstrate the overall RI construct validation test reports for the mappings extraction and generic extraction with the version of 2020 April. As you can see, we achieve an RI test coverage of around 87%, and based on these tests, we have an error rate of 0.25%. We also evaluated external datasets to check for the reusability of these defined test cases and assume that we can use it for the checking of correct backlinking to DBpedia RIs or the usage of correct schemas or ontologies in these external datasets. For calligraph and geoname, we also could show that we have erroneous data, and this can be related to the wrong usage of DBpedia RIs in these data artifacts. The next level I want to demonstrate is the syntax validation and pruning approach, and therefore I want to distinguish that in RDF parsers we have errors and warnings. Errors are mostly fraudulent statements that contain irreproducible information, for example a syntactically incorrect triple, and warnings just can be incorrect formats, for example for data type literal, the incorrect format of the date. In the pruning step, errors and warnings get removed, and this guarantees a better enjoyability in the target software due to strict parsing of some databases or other software. If we compare the triple count between the Marvin pre-release and the final DBpedia release, we just lose about 4% of the produced triples. Finally, I want to give a quick example how an integration test can work. Therefore, I have a query that checks for the completeness of the mappings group release on the DBpedia databus. For example, the mappings-based instance types group should contain 80 files, therefore 40 files for the normal instance types and 40 files for the transitive instance types, and this query compares each version and artifacts with the actually produced files on the DBpedia databus and the expected files in this query. Based on the introduced testing methodology levels, we hope that we derive better statistics about the evolution in quality in the DBpedia releases in the future. But at the moment, the most important achievements are the process automation. For example, you can find a fully automated DBpedia extraction setup at the Git repository. The next one is the improved testing methodology with the Minidump and Large-scale Validation, and also the better access of the reports and issues to the community, as well as the better access to the data itself. In the next steps, We want to provide an extraction progress monitor, and the prototype can be already found at release-dashboard.dbpedia.org, and it shows the current time, current step and extraction logs of the current release. And for the integration tests, we also want to aggregate more statistics about the produced data at the DBpedia Quality Dashboard. Thank you for your attention, and if you have any question, don't bother to visit our forum.